I remember standing in Rome one time, just staring up at the Lateran obelisk,
Oh, yeah, the big one.
the big one, and it's this single flawless piece of granite, 455 metric tons.
That's right.
And the thought that just hit me was, how? How did people thousands of years ago carve that, move it, and then stand it up without a single steel crane?
Right. Seems impossible.
So that's our mission today. We're going to dive into the geometry and the incredible mechanical secrets of the ancient Egyptian Tetekenu.
And to really get a sense of that ambition, you have to look at their limits.
Okay.
The unfinished obelisk at Aswan, it's huge, about 1,090 tons, over 41 meters long, and it's still there, cracked in the bedrock.
So it's like a frozen experiment.
Exactly. It shows us exactly where their technology hit its limit, but also where their planning was at its absolute peak.
So let's unpack that. I mean, these weren't just decorative sculptures, right?
Right.
They had a really profound religious meaning.
Oh, absolutely.
Yeah.
The obelisk was a symbol. It was a petrified ray of the sun god Ra.
A petrified ray. I love that.
And it all culminates in that pyramidal tip, the pyramidion. That symbolism is what drove the engineering. They had to be tall, slender, monolithic.
Which demands some serious mathematical precision.
It does. They relied on practical, empirical knowledge. Architects used concepts like seeked, which is basically their version of calculating slope.
So they could standardize the proportions.
Precisely. And they kept this very specific slenderness ratio, usually about 10 to 15 times taller than the base is wide.
And that wasn't just for looks.
Not at all. It's structural. Go beyond that, and you're seriously risking buckling failure. It's knowledge that's been resisting gravity for 4,000 years.
It's incredible, especially when you think they did all this with hand tools. How did they even get these giants out of the ground?
The quarrying alone was a monumental task. You had thousands of workers hammering away at the granite with these hard stone hammers called dolerite balls.
So just chipping away bit by bit.
A painstaking process. You can still see the pecking marks today. And once it was carved, well, then the real logistical challenge began.
The overland movement, that just sounds impossible for a 400-ton stone.
It's all about organized systems. They'd get the giant stone onto a sled and then pull it across these lubricated tracks.
Lubricated how?
Think wetted clay or mud. It just dramatically reduces the friction. Then it was onto the Nile on these huge purpose-built barges.
Okay, this is the part that always gets me. No cranes. They get this massive horizontal stone to the temple. How in the world do they stand it up?
The answer is it's controlled gravity and simple machines.
Levers.
Class 1 levers for the initial lift, yeah. But the real secret, which experiments have supported, is the sand mound method.
A mound of sand.
A huge, precisely built sand ramp. The obelisk would rest horizontally on it right over its final pedestal, and then they'd slowly, gradually remove the sand from underneath the heavy end.
Ah, so it controls the rotation.
It turns this massive, dangerous problem into a gentle, controlled pivot. The obelisk just slowly rotates down into place.
That level of coordination is... It's just phenomenal project management. It actually makes you think about the kind of large-scale projects we tackle today. Maybe you're not moving 1,000-ton granite blocks.
Let's hope not.
Right. But you're probably facing some really complex integration challenges. And actually, this deep dive is sponsored by Silk. If you're navigating the modern logistics of technology, say, you need help with AI training, automation, or just figuring out where AI agents could make the biggest impact for your business, you should check them out at embersilk.com for your AI needs.
You know, that ancient understanding of simple, robust design, it still influences us. Look at the Ramses II obelisk at the new Grand Egyptian Museum.
Right.
Even though that design has proven itself for 3,000 years, modern engineers still installed state-of-the-art base isolators underneath it.
Base isolator, so like shock absorbers for an obelisk. Why if the design was already so good?
Because modern standards have to account for, catastrophic but rare events, like earthquakes. The isolators decouple the structure from ground vibration. It's this fascinating moment where ancient builders used mass and proportion for stability, and modern engineers add complex systems to protect it from extreme threats. It's ingenuity building on ingenuity.
So what's the big takeaway for us here? It's just this powerful testament to applied simple physics.
It is.
The geometry they developed was so fundamentally sound that it's just worked for millennia. It proves that basic ingenuity is often the most enduring solution.
It really shows that these huge, complex problems, like moving a mountain, can be solved with elegant, disciplined thinking. It's a pretty incredible lesson in human persistence.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.